I guess that's my cue of starting the class. We can wait for another. Yeah. Why are you here? You probably already know these. Yes. Uh-huh. Uh-huh. There should be. Okay. Thank you. So good morning, everyone. Thank you very much for coming all the way to Hawaii to come to my lecture. I apologize that my voice is a little coarse because I'm having a cold, but I try to not be contagious to you guys. If you have any questions or if you cannot hear me clearly, please feel free to stop me in the middle of the lecture. So today we're going to talk about some basic concepts on hypothesis testing and especially with the focus on two sample tests. And we'll go over one sample testing, two sample testing, and we'll also go over some basic functions and ways to calculate power and sample size. So before we get into the testing, I would like to first introduce a few basic concepts. So what are hypotheses? For statisticians and for scientists in biological or medical field, hypothesis may have very different meanings. Many of you guys may use hypothesis to refer to a statement that gives a desired answer to your research question. For example, is A associated with B, or is certain group performing better than the other group? However, those languages need to be translated into a statistical hypothesis that is formatted into a statement regarding certain parameters so that you can use statistical tools to verify your hypothesis. Here are three examples. In the first case, we have an antiretroviral drug that may or may not change the LDL after the treatment. So the research question is, does LDL change from baseline to 24 weeks after the treatment? That's your research question, and it can be translated into multiple statistical hypotheses. For example, by changes, do you mean the maximum change, the minimum change, or the median, or the mean? There can be many ways. And here, the most common way to translate this kind of question is through modeling the mean of the change. So the research hypothesis can then be translated into a mean parameter of the distribution of the LDL values. Here, this mu is used to denote the population mean. This will be a parameter that's unknown to us, and we'll use data to infer whether this hypothesis is true or not. And your alternative hypothesis can have multiple formats. Here we have a two-sided test. You can also have a one-sided test. For example, if you know that the LDL can never be decreased, then you can use an alternative hypothesis that's only one side. Mu is larger than 0. And the choice of the alternative hypothesis really depends on your context of the research question. So in the second case, we have two antiretroviral drugs that we want to compare. And in this case, we'll have two parameters. One for the mean of population 1, one for the mean of population 2. And we'll take samples from each population and use those data to test the hypothesis here. Of course, you can have another alternative hypothesis where you assume that one drug is definitely going to have larger effects than the other drug because, for example, one drug may be your placebo. Then in that case, your alternative can be a one-sided alternative. And in this third case, instead of a mean parameter, sometimes in our research, we also deal with a proportion parameter. So this is one example. The research question is there a difference in the HIV control between those who adhere to their medication and those who do not? So you would have a proportion of people who get infected, who get the viral load detected, and that proportion is your parameter of interest. You want to know if this proportion is different between two groups of people, and in that case, you will have null and alternative hypothesis in terms of the proportion parameter. The proportion and the mean parameter are one of the most common parameters that you use in your research, but in some cases, you can also have variance parameter. For example, in one of my research projects, the investigator is interested in whether the heterogeneity of the gene expression is going to affect how the patient responds to the cancer treatment. In that situation, you would want to test if the two groups have their variance different from each other. So there can be multiple ways of formatting your null hypothesis, be open-minded to it. And so now we have some examples. I want to go a little bit abstract. We are going to define null hypothesis and alternative hypothesis and discuss their difference. So why would we put certain things in the null hypothesis and the other things in the alternative hypothesis? In this case, one, for example, why don't we put mu not equal to 0 in the null and alternative as the mu equal to 0? It actually really depends on what your null hypothesis and alternative hypothesis mean. In general, we put the status quo in the null hypothesis. It's like in the US legal system, your defendant is assumed innocent until proven guilty. So we would want to put the conservative hypothesis in the null. And we will need to be very careful about our rejection so that we don't, we want to control the error we make, the kind of error that is rejecting the null when the alternative is true. So you don't want to easily reject the null hypothesis. For example, if in a drug efficacy study, you want to put drug is not useful in a null hypothesis. And if you want to test the drug safety, you want to put the drug is toxic in the null hypothesis, because the cost of making a wrong decision here is different. If your drug is safe and you say it's toxic, it is not going to hurt your patient. It's going to hurt the drug company, but your patient's priority is higher. And in the drug efficacy study, you don't want to say a drug is effective when it's actually not, because that's going to cost the health system by a lot of money. So that's why we put the status quo, the more conservative one, in the null hypothesis. Any questions? And because the null and the alternative, they are not really symmetric, we put more emphasis on the null. And that's why we also make errors that are treated asymmetrically. There are two types of errors. You probably already heard about them: type 1 and type 2 errors. The type 1, sorry. So I'm going to put it here. It's in the lecture, but it's too small to see. So there are wrong decisions here and the right decisions on the diagonal. When the null is true and you reject the null, you make type 1 error. When the alternative is true and you fail to reject the null, you make a type 2 error. Because we treat the null and the alternative asymmetrically, we also treat the type 1 error and type 2 errors asymmetrically. Those two come in together. We want to make type 1 error as small as possible. So we actually later when we talk about statistical testing, we are actually going to make sure that this type 1 error is controlled below a level, and we'll go with the test that has type 2 error that's as small as possible. So we don't really know what type 2 error is in our data, but we want to make sure that type 1 error is under certain control. And the number that we use a lot is the 0.05. So in many of the tests, you actually don't really know what the type 2 error is, but you know the type 1 error is under control, and you feel safe because your null hypothesis is the one that you really care. And we will use alpha to denote the probability of making, why is it smaller? So we'll use alpha to denote the probability of type 1 error, beta as the probability of type 2 error. And 1 minus beta is the thing that you really like, the power to detect the the signal in the alternative hypothesis. We would love to have both alpha and beta to be small. That would be a very good statistical test. But in reality, there's no way that you can decrease alpha and beta together because there's uncertainty involved in your data. When you collect data from a population, those randomness involved in the data generation, that will make you make errors. There's no way that you will not make any error if your data has randomness in there. And you will either make type 1 error, type 2 error, or both. There's a trade-off between those two. And the trade-off that we make, the compromise that we make, is to make sure alpha is under 0.05, and beta will try to make it larger, smaller. The power will try to make it larger. So that's this statement. And in the drug efficacy example, when you make a type 1 error that's concluding the drug is effective when it's not, this is the error that's costly, and you want to control it below 0.05. The type 2 error will be concluding the drug is not effective when it is actually effective. You miss a good drug, but it's not going to cost a lot of patients money and time. So type 1 error, you still want it to be small, but it doesn't matter if we don't know much about it. So that's the difference between type 1 error and type 2 error that come together with the asymmetry of the two hypotheses. And you also have the asymmetry of the rejection and non-rejection. So when you have when you have a p-value that's smaller than your desired level, when you reject the null hypothesis, you can conclude that we have enough evidence to show the alternative is true. But when you don't reject, it doesn't mean that you have enough evidence that the null is true. It just means that you don't have enough evidence that the alternative is not true. So it's possible, it's entirely possible that when you do one test with a sample size of 10, you don't reject the null hypothesis. But when you increase your sample size to 100, you have enough power to detect the difference, and you will reject the null hypothesis. So when you have the sample size 10, you don't reject, it doesn't mean that the null is true. It just means that you don't have enough evidence to say either one is true or not. And test statistics. This is the tool that we will use to reject the null or not. So what is a test statistic? It is basically compiling all your data points into one number. The mean of your population, that's one number. The proportion of your the patients that has a detectable viral load, that's your test statistic. So it's just one number that's representing the data and reflecting your hypothesis. There can be multiple test statistics associated with just one hypothesis. So there are bad ones, there are good ones. The Z test and the likelihood ratio test, those two are two of the most common tests that you can see. So when you, in your elementary stat class, the mean plus minus 2 times standard deviation, that is actually the Z test that uses some assumption on the data set, but there can be other tests doing the same thing. So we will only talk about the most common tests, those that is used for the hypothesis involved here. When you have a test statistic, it's going to be a random variable. It's a little confusing because you already compile your data into this one number. The mean of your 10 sample, that is going to be, for example, 2, and that's one number. How is it a random variable? But if you do another sampling, get another 10 patients and calculate a mean, it may not be 2 anymore. So that's the randomness involved there. And in order to know whether 2 is too large to reject or too small to reject, you need to know by resampling your patients how this number is going to change. What is going to be the distribution of this mean? And you will be able to know whether 2 is too large or too small. So we will need to know the distribution of the test statistics under the null hypothesis. And this distribution may not always be known to you because who knows whether your distribution is a normal distribution or not. You may have a violation. But when we say distribution, many times we use a large sample distribution. So it means that if you have a large sample size, then this test statistic will have a distribution that's in certain shape. For example, normal distribution, chi-square distribution, F distribution. Those distributions actually mostly rely on the large sample assumption. So be careful when you use those tests because it often assumes the large sample size. And when you have a small sample size, it's more reliable to use non-parametric tests where the distribution of the test statistic don't rely that much on the distribution of your data set. So now you have a test statistic, you know the distribution of the test statistic, you will check where your observed value, the number 2 of the mean of your 10 samples, where that is located in your null distribution. So you can construct an acceptance region. This will be the set of values where your test statistic will fall such that you don't reject the null hypothesis. And so the twin, the twin of acceptance region would be the rejection region. It's the complement. And if your test statistic is in that range, you will reject the null hypothesis. So for example, if you have a Z test that's 3, it's larger than 1.96. The larger than 1.96 is actually your rejection region because 3 is in the rejection region, we reject the null hypothesis. And this acceptance region is often connected with the confidence interval. So in some of the statistical classes, you will learn about how to invert a confidence interval to get acceptance region and vice versa. But I want to tell you one thing that's different between the confidence interval and the acceptance region. So a test acceptance region and rejection region, that's about the test statistic. The confidence interval, this is about the parameter. So you check if a parameter, your null hypothesis, is inside the confidence interval. You check if your test statistic is in the acceptance region or not. So those two are related, but they are two sides of the same story. Any questions? And so z-test is one of your test statistics. P-value is also one of your test statistics. Because if you look at it, you have a bunch of data points, you use some test statistic, and you calculate the p-value. This p-value is also a compilation of your data points, right? You transform all of your data points into one value. So this p-value is also a test statistic. It's very special because it also tells you whether your data is too extreme for your null hypothesis. And by extreme, we mean extreme in the direction of the alternative. So here are some examples. Suppose we're testing the mean of LDL change. Null is not changed at all. The alternative can be changed in either direction. And by more extreme, we would want to see an observed mean that is very large or very small. So under the null hypothesis, if there's no change, your y bar shouldn't be very large or very small. In the direction of the alternative, if your data is too extreme for the null, then y bar is either too large or too small. Those two extremes are both extreme in the direction of the alternative. So the two-sided is more straightforward. For the one-sided, it's a little hard to wrap your head around. So suppose your alternative is mu smaller than 0. The change is you have a decrease in LDL. Then more extreme means that your data is actually smaller than what you observe. So you would want to reject the null hypothesis when your mean is very, very small. If your mean is very, very large, that doesn't mean that it is too extreme for a null, because in this situation, you never really consider mean increasing. You only consider mean decrease or stay unchanged. So the direction of more extreme means that y bar is actually too small for the null hypothesis. And for this one, by too extreme, we mean that y bar is too large for the null hypothesis. So your p-value will reflect the alternative. You will have a p-value that's different for each one of them. In the first case, your p-value is the probability of observing a y bar that's even larger than the absolute value of your observed mean, or smaller than negative of this mean. In the second case, your p-value is the probability of observing an even smaller number than the observed y bar. In the third situation, the p-value is the probability of observing a y bar that's even larger than the observed y bar. Your p-value is the probability of observing a data set that's even more extreme, that's too extreme for your null, and you will reject the null hypothesis when this probability is small. So that's why we most of the times when we use p-value as a test statistic, we reject it so that it's smaller than the type 1 error rate that we want to control. And there have been a lot of discussion in the medical world about why we're using 0.05 as the type 1 error control, why not using 0.1 or 0.01? Well, there's really nothing special about 0.05. It's just one of the most famous statisticians about 100 years ago decided that this is a number that he wants to use. and it's becoming a tradition. But you can definitely choose other alphas depending on your tolerance about the type 1 error. So if you want to be very conservative, you can choose a type 1 error that's smaller. You can say that the drug is effective only when your alpha, when you reject the null hypothesis when alpha is 0.01. In this situation, you would feel better about not making any large type 1 error. So the p-value actually really just reflects your tolerance about the type 1 error. It means that when you have a small p-value, it means that your effect, the alternative, the evidence of the alternative is so significant that you cannot you can actually reject the null hypothesis with a type 1 error that's smaller than its p-value. So you the smaller type 1 error makes your rejection having a smaller probability of making a type 1 error. Any questions? So here we have gone through all of the basic concepts of hypothesis testing. And then we'll use some examples, the one sample test, two sample test, to go over the hypothesis testing steps. In summary, you would follow all of these 5 steps. First, you will need to know about your data, the type of data, the study design, whether it's paired or unpaired, whether you have continuous distribution of the data, count data, whether the distribution of your data is normal or exponential distribution. You may have only positive continuous values, or you may have both positive and negative. You might want to do some transformation, for example, log transformation, exponential transformation, things like that. So that needs to be done before you post your hypothesis. And then you can set up the hypothesis and choose the significance level alpha. This needs to be chosen ahead of time, because if you see the p-value and then choose alpha later, you're in the danger of cherry picking. And then you would choose a test statistic. Many of the times you only use the most popular one, and you calculate the value of this test statistic by plugging in your data and calculate the p-value associated with your null hypothesis and alternative. And you can sometimes confidence interval comes handy because it helps you interpret the results better. And then you would draw the inference based on all of the values that you obtained. So let's go to the one sample test. Here we will focus on the normal distribution. Suppose that we are still looking at this change of LDL after the drug treatment. Here we can look at the type of data. The LDL comes in continuous numbers. So we will not be using count distribution. You can check the mean, the quantiles, and you can also check the distribution by using histogram, box plot, violin plot, density fit. So I have all of the codes here to help you replicate the plot here. And in this situation, it looks relatively bell-shaped. You may argue that it's not, but since this also has a very large sample size, we'll just go with the normal distribution. And here we also look at the study design. So this is, you just take cross-sectional samples, and that means you have the baseline, you have the measurement after the treatment, and you take the subtraction. So this subtraction, this difference will be your observed data. The change in LDL is your observed data. And the null hypothesis means that the mean of this change is 0, and the alternative is the mean not equal to 0. And then we would calculate, so we talked about the distribution. I said that it looks relatively bell-shaped, but you actually have a test to verify it. You can use QQ-plot, and there's also a statistical test for checking normality. But I find QQ-plot more useful because often when you use the statistical test to check for normality, you overlook where the violation of the normality come from. And you also sometimes forget about the sample size when you just look at the test. By looking at the QQ plot, you will know if it's caused by a few data points or it's just a small sample size. Or by looking at the QQ plot, you may also come up with a good transformation of the data so that after transformation, your data will be more normal-like. So I prefer normal QQ plot to look at the to check the normality. So has any one of you guys learned about QQ plot before? Right. So if you have data points that follow the straight line here, it means your data is relatively normal. If you have a C shape or a U shape, those are violations. A S shape, those are violations of normality. And there are transformations customized to each one of those cases. You don't have to remember those. You can always Google. And so here we have pretty normal data, so we'll just move on to the test statistics. Sorry. So I jumped too quick. So after we know about the data, we come to the hypothesis testing, a very short but the important step. We now know that what is our research question and what is our statistical hypothesis. And when you really write this out in terms of words, you will know what your conclusion. It will be clear what your conclusion is when you have a rejection or not. And then the test statistic to use for this normality situation when you have normal data is going to be a t-test. So the z-test is just a large sample approximation of the t-test. When your sample size is super large, it's safe to use z-test. But since t-test is not that hard to calculate using R, we would use t-test to be safe. So the t-test has numerators that reflect your null hypothesis. You want to check if the mean is too large or too small compared to 0. Mu 0 will be the null hypothesis, the mu under the null hypothesis. So you take the difference. You want to see if this is too large or too small. But how large is large? How small is small? If you use, for example, milligram as your unit, it's one number. If you use gram as your unit, you have another number. So how large is large? That is going to be scaled by the denominator, which is the standard deviation, which includes the standard deviation of the data. So if you have different units, those will be canceled out between the numerator and the denominator. And you will be able to know how large or is large for y bar by looking at this ratio. And you will reject the null hypothesis when this is too large or too small for the two-sided test. And this ratio is actually a t distribution under the null hypothesis. So the degree of freedom of your test is going to be related to your sample size. We have all the formula here, but I know that in reality you guys just use R. This is just to get you have some sense of what is behind the software. So why we have the numerator and the denominator and what this test statistic mean. And so when you have the value of the test statistic, for example, the t-test here, you will compare it to the distribution, how this value should distribute if you keep resampling. and if your population is under the null hypothesis. So this will be the distribution of the t. It will be the distribution of the test statistic under the null, and you will see where your observed value is located. So if you observed a value 3, it will actually be over here. So that's a very small chance to happen. If this is truly your null hypothesis, then observing a 3 means that you have a small chance event happening, and it's unlikely that your null hypothesis is true. Likewise, if you have a super small value, you would want to reject the null because it's a small chance probability to have event to happen under the null. And so that's why in between those 1.96, 7, this red region is your acceptance region. It is used to compare your test statistic with. And so here we have the distribution. We calculate the value. In this situation, the mean is actually 2.23. We have the standard deviation. When we calculate the t-test, is not very large. So in this situation, we don't reject the null hypothesis, but it doesn't mean the null hypothesis is true. So you may say that, wow, we have 262 patients. That's a pretty large sample size. How are we going to say that the null hypothesis is not true when you don't reject it with such a large sample size? Well, the truth is you may have a very, very heterogeneous population that 262 may not be large enough. So that's one possibility. But chances are the larger your sample size is, the less likely you make a type 1 error, and the more likely you will have a high power. So when you have a very, very large sample size, a very homogeneous population, a very strong effect, when you do not reject the null hypothesis, it's very likely, it's very tempting to say the null hypothesis is true, but you don't make that conclusion. The rigorous way is still to say that even with such a large sample size, even when you have all these good natures of the data, you still do not have evidence to reject the null hypothesis. So that gives you confidence on the null, but it doesn't tell you the null is true. And so when you make the conclusion, you say there's not enough evidence to reject the null. I have the most useful tool for you guys, the t-test here, that you will probably use instead of the formulas above. So here, this test function will be used for both one sample and two sample t-test. When you have one sample t-test, you just put the x, your data as the input for x, and y you can leave it as null, and you can choose whether to do two-sided test, or your alternative is mu smaller than the null hypothesis, mean smaller than the null hypothesis, or mean greater than the null hypothesis. This is the direction of the alternative. And this is the value for the null hypothesis. It doesn't have to be 0. So sometimes you may have a scientific question where you want to see if the LDL or the efficacy of your drug is larger than, for example, 1. Where do you come up with this 1? The 1 may be based on some previous studies where another drug, an existing drug, is already used. Suppose you have a lot of large population studies where drug A is shown to have an efficacy of 1, and you're testing if your drug 2 works. Then you may not need to have drug A in your trial by just formatting the hypothesis, null hypothesis, as mu equal to 1, and just collect data for the treatment under your drug B, a new drug. In this situation, you are just comparing your drug with the mean of the previous drug that you think you already know very well. So this null hypothesis, it doesn't have to be zero. It can be based on previous evidence. If you can, if you have a very strong case to advocate, so the mu doesn't have to be zero. And this paired option is used for two sample tests. This is also used for two sample tests. And you can also choose the confidence level of your confidence interval, because this thing is going to give you a confidence interval. By default, it will be 95%. So here I have the code. You just input the vector of data. This will just be a vector of values in R. And in the output, you will have the test statistic, the degree of freedom of your test. This is actually your sample size -1. And you have the p-value, the confidence interval for the mean. And this is the two-sided confidence interval. And you also have the sample mean. Any questions? And so here in this test, we have the normality assumption, but in some situations, your data is just not normal because, for example, if you look at the proportion, it can never be a normal distribution. That's why we have other tests for the non-normal distributed data. But if you have, for example, exponential distribution for non-negative values, or Poisson distribution for counts, if you have a very large sample size, it can still be safe to, it is sometimes when your sample size is large enough, it is still safe to use this t-test to check the mean. Because we have the central limit theorem, the Slasky theorem, those things will guarantee your test is still valid in terms of large samples. So you need to have a large sample size to use the t-test for non-normal distribution. But how large is large sample? Well, it really depends on case by case. So if you might need a even larger sample size if you have a more heterogeneous population. And for binary data, for proportions, you can also actually use the mean, the t-test, as a way to compare the mean parameter, which is actually the proportion parameter. But this, since we have more exact tests, so this is just some rule of thumb. So if you have a proportion and suppose you're in the bar making an argument with someone talking about the proportion of getting infected by COVID after taking the vaccine, and you have the proportions, you can do a simple calculation in your head like this to see if you can win the argument or not. But this is rarely used in research now. So if you do have a population proportion, what do you use? So here I have about 300 individuals where we want to see if their virus load is well under control. And we observe that about 37% of them have the viral load under control. So when you look at this result, make sure you know both the proportion and the sample size, because your test is going to depend on both. If you only have the proportion and not the sample size, you don't really know how strong your evidence is. You can have two flips of coin and both heads. It doesn't mean your coin is biased. So here we are going to calculate the, well, we'll go back a little bit. So let's go back to check the data first. The data has a Bernoulli distribution or a binomial distribution, that's another name, where you have the proportion parameter, that's the population parameter. That's pi, and the sample size is 300. And this is a proportion of having patient not under control, and this is under control. So you can use your rule of thumb, but this is really large, so you would reject null hypothesis and say that oh, by the way, so this rule of thumb here, pay attention to the pi zero. This pi zero is actually the, so this pi zero is a null hypothesis. This rule of thumb, sorry, I probably need to go back to my argument here. So this rule of thumb is actually to say whether your sample size is large enough to use the normal test for proportion, testing of proportion. This pi zero is your null hypothesis, so it will be 0.5 instead of the proportion you observed from your data set. So this is just to check if your sample size is large enough to use the normal approximation. It is satisfied here, so you are safe to use t-test. But we're going to do a proportion test based on the binomial distribution. So here I have checked the data. The sample size is large enough. Its distribution is clear. And in the second step, we format the research question into null versus the alternative. The null is going to be 0.5 because we want to see if the proportion of individuals who have viral load control is more than or less than the proportion of patients who do not have viral load under control. And you can use different pi zero. If you want to test, if you know that the proportion of patients who are going to be under control is a much larger value, and you are trying to see if it's going to be even more improved by your drug, then you can choose a pi zero that's different from 0.5, and your alternative can be a one-sided alternative. But here, for simplicity, we're just going to check if the viral load control is going to be a flip of coin. And in the third step, I'm going to use this mean to, the proportion is actually the mean of ones among all the 0 and 1s. So the mean here is the proportion. We can use either p hat or y bar to represent it. But p hat is more straightforward. It's the proportion you observe from your data. And you can use normal distribution to approximate it and use z-test. So this is going to be the large sample test. It is under the assumption that your sample size is large enough. But in R, we have another test that's going to be exact. So that one doesn't assume your data to be normal or your sample size is large enough. This is the test that you can do in your head when you get into an argumentative R. So this test will have the mean, the difference between the observed proportion and the proportion in the null hypothesis. This difference will, if this is large or if this is too large or too small, you will reject the null hypothesis. And similarly, we would want to scale it by the variance of the data. And the variance of the data is related to the null parameter here. So this is just scaling to make sure the test statistic, the difference is reflecting the homogeneity or heterogeneity of the data. And the z-test statistic here, if it is too large, too small, you reject, and apparently it is too small here, so you will reject the null hypothesis. And you can also reject null hypothesis based on the confidence interval here. So the confidence interval here, it doesn't contain the 0.5, which is your null parameter, so you would reject the null hypothesis. And when you use the confidence interval, you are essentially also using the type 1 error rate that's related to the confidence interval. So if you use a 95% interval to do the rejection, it means that you're trying to reject when your p-value is smaller than 0.05. If you have a confidence interval that's 99%, that means you're trying to reject null hypothesis by controlling type 1 error under 0.01. Those two coming together. So when you, in some research papers, they will provide both 95 and 99 confidence intervals. Using each of them reflects different type 1 error control. And here we have the p-value, but the p-value is very small. So whenever either using a 0.01 or 0.05 for alpha, you will reject the null hypothesis. It means that the evidence for the for the alternative is so strong, you will reject the null hypothesis and go for the alternative. So here I'm going to show the code for doing this test using R without assuming the large sample assumption. So the binom test here, you put your vector inside the sum. If you just have the proportion, you just put the proportion here. You have the proportion here, you have the sample size here. But if you have a vector of 0 and 1, you put the mean in these functions to get the sample size and the mean. And well, actually not mean, it's the sum. So if you have the proportion, you need to multiply the proportion by the sample size to get the number of positives, number of people who are not under control. And your null parameter 0.5 is here. You can choose one-sided test or two-sided test here. And in the output, you will have the confidence interval, the probability of success, the sample size, the p-value, and this will actually you are safe to use this function when you only have 10 or 5 samples. It's still safe. So since the p-value is too small, we're going to reject the null. Any questions? Do you like, yes.
Can you explain again why the x is the sum of the?
Oh, yeah. So this number is actually going to be 119.
Okay.
So out of the 318 subjects, you have 119 that's positive. The rest are negative. 119 are 1, has value 1. The rest of the patients have value 0. So if you take some of them, you will have 119 here. And this n will actually be 318.
Thank you.
Thanks for the question. Any other questions? Do you guys want to take 2 breaks or 1 break? I guess we'll just take 2 breaks of 10 minutes instead of 1 break to give you guys more room to move your muscles. We'll come back at 10. Not separate?
No, the confidence.
Oh, okay.
Isn't that only related to the hypothesis test on constructed under the null?
Right.
Wasn't it? Did you say that?
Well, actually, not really. So,
well, like you could come up with like examples, right? Where P hat versus P null. Like it holds the null.
the confidence interval is related to the alternative, but
Right.
yeah, but the number for now, it doesn't really change the confidence interval.
Yeah, no, yeah, because I thought, well, you said that but I think you said that the confidence interval, since it doesn't include the null, you could reject, I thought you said that, but did you?
Maybe I made some confusing statement.
Okay, all right.
Can you say it again, because I
No, I thought that you said that the confidence interval could also be used to reject the null, because it didn't include the null hypothesis, like 0.5.
Because the null parameter is not inside the confidence interval.
But I was saying, I don't, and I think like normally that's true, but I think you could really only say that the confidence interval was constructed using the null. So like when you did the standard deviation, you use p hat instead of like 0.5.
Oh, actually, you can also, well, I see what you mean.
Yeah. I think it's like super rare.
Well, it's just a bad confidence interval to use.
Yeah. It would still not include it, but yeah.
Well, yeah, when you use, well, so the confidence interval that's used for the situations here, they are going to be the mean parameter plus minus the standard deviation.
Right.
And that standard deviation has to be
Right.
the plugin data instead of the null.
Right.
Yeah. But for the proportion test, I think what you're mentioning is this one.
That's fine, yeah. No, I was saying, I felt like you said, so if you scroll down, like, no, scroll up a little bit, like, right, down, a little down. Oh, other way.
Here?
Other way, a little bit more, and stop. No, I was just saying for that p hat. For that to correspond to the test, it has to be 0.5.
No. This is the plugin of this has.
Yeah, and so I know it's normally the confidence interval. But
Right.
I'm saying like if you wanted to construct the confidence interval under the null.
Well, that's not really.
Yeah, it's not really.
Well, it doesn't matter what your null parameter is. This is going to be the confidence interval.
Yeah. But like for it to correspond to the test, it would have to.
No.
So the standard deviation is based on the p hat instead of the null.
The standard deviation is based on the p hat, so that's why it's safe to use for whatever.
Right, for the confidence interval, yeah. Which normally corresponds to the test.
So if you're, well, I guess so suppose your null hypothesis is p equal to 0.2.
Right.
Then you will reject the null hypothesis here.
But I'm saying you couldn't use the confidence interval because the confidence interval wasn't constructed under the null. It's like a separate thing. Like if the confidence interval doesn't include 0.2, it's just the because it's not the same as the test.
I see.
Because it wasn't constructed under the null.
Well,
it's like a really. I'm sorry.
Yeah. You're right.
That's all I was saying. I think like and we all do it, right? And especially with like.
Actually no. No. I can. I'm trying to get my head around it. So the test is going to be p. Well, it's going to be this pi0 over square root p hat 1 minus p hat.
But that's not the test, right? The test has to be under p.
Well, with that, it's very difficult to reverse to a test because to a confidence interval because it's hard to solve that pi0. It has the square root, all the things in the numerator, denominator, so it's very hard to solve. And that's why we use this test. This is the test that corresponds to the confidence interval here. And we would construct the confidence interval by comparing this with 1.06 and negative 1.06 and the 996, and then we solve for pi0 to get p hat plus 1.96, this whole square root thing. So this is the parameter of the null, no matter what it is. But we're going to use this interval to check whether this is inside.
But I think for this example of the proportion, though, the standard deviation is tied to the null swap.
No. You can, well, the interval here is related to this test, not the test above.
Right. So yeah, I think the interval isn't itself, I guess, because it's not constructed with the null. It's okay.
So let's say the pi zero is 0.2. So
I think
the pi, this thing larger than 1.96 is equivalent to saying that 0.2 is outside of this interval.
Yeah, but I'm saying that has to, you would have to have 0.2 in the denominator.
No, there's no 0.2 here. No 0.2 here. The 0.2 is only here.
Mm.
So we
oh, I see what you're doing.
Yeah. So this test there, that thing is a bad test to construct for the condensable.
Well, you can't. Yeah. Well, that's okay.
Yeah, because it's super hard to solve for pi zero.
Mm-hmm. Okay. Yeah. No, we're good.
Yeah. But it's right that when you use condensable to reject the null hypothesis, you need to use the right one for the right alternative.
Mm. Okay, we're good.
So Richard raised a very good question that reminds me that I need to clarify something. So when you use confidence interval to reject the null hypothesis, it doesn't really matter what your null hypothesis is, but it matters what your alternative is. If you have a two-sided confidence interval, it is related to a two-sided test, two-sided alternative. You cannot use a two-sided confidence interval to reject a one-sided alternative hypothesis. For example, here, you have the two-sided confidence interval that's 0.3 to 0.4. Suppose your null hypothesis is 0.2, and your alternative is two-sided. You can reject the null hypothesis. But if your alternative is one-sided, you do not necessarily reject the null hypothesis using this interval. You need to get the one-sided interval that corresponds to the one-sided test. Does that make sense? So suppose we have alternative that is p larger than 0.2. The alternative. So suppose I have null that's 0.2, alternative that is smaller than 0.2, and you have a confidence interval that's like this. Can you reject the null hypothesis? Because this is just for two-sided test, right? Even your 0.2 is out of this, even if you're so here it is actually the opposite. Your observed evidence is actually much larger than 0.2. What if your alternative is p larger than 0.2? Can you reject the null hypothesis? You have a very strong evidence that the p is going to be between 0.3 and 0.4. Can you reject the null? Very likely you can, but you need to redo the confidence interval to make sure. So that's the one sample testing, and we'll talk about the two sample test when you try to compare the distribution of two populations. And by comparing the distribution, we're just comparing the mean parameters. And we will first assume that the two populations, they have the same variance. In this situation, the two sample t-test with equal variance will be used. Our parameter of interest will be the difference between the mean parameter, and naturally you would want to plug in your data and use the population mean and of the two groups as your test statistic. Your intuition is right. This difference is going to be the key component of your test, but you need to know how large this difference is by comparing it with the distribution, and you will also need to scale it by the variance of your distribution. So that's why we'll also have the variance calculated and use the variance in the denominator. So the distribution of this difference is going to be a normal distribution if your data is normally distributed, and you will plug in your data to get the estimation of all of these parameters. And the confidence interval of this difference can be constructed using all of these plugins as well. So here we are calculating basically the sample variance, the population, an estimate for the population variance by plugging the sample variance of each group, and your confidence interval for the difference will just be the difference plus minus some value multiplied by this variance, the standard error of the mean. So this will be the standard error, and the instead of 1.96, you will have to look up the t-table, a nightmare for the undergraduate stat student, or you can use R to find it. And you also need to know the degree of freedom for your t-test. So here I have two groups under two different treatments, and we're going to check if LDL change is different between the two groups. They can be two groups such as two gender or two age groups, or two groups under different drug treatments. And I'm summarizing the distribution of the data again using this density plot is basically the shape of the histogram in a finer format, and checking the normality of the distribution using qplot. This is okay, not too bad. For the other group, we're going to use the same checks. Yeah.
So, like, is this the best way to do it, or would, like, I've heard of people do something like a normality test.
Yes, yes. So normality test is very useful if you have to use it to choose a distribution, but it's not as informative as the QQ plot, because QQ plot can also let you know why your normality is violated, because you may learn from the shape of the QQ plot and choose a good transformation of the data to get your data normal.
Would you say you would always first look at the QQ plot, and then, like, in what case would you actually try to use it?
I barely use the test. Yeah.
Okay, so as long as it looks like a straight line.
Yeah. Yeah. And many of the situations, even if you have a violation by a little bit, the thing is, you need to know what to do next, right? If you have a rejection of the normality, what to do then? So a Q plot can give you that. And then for confidence intervals, we will plug in all of these numbers. Fortunately, we don't have a test for this course, right? You don't have to write these on a cheat sheet and plug in cruncher calculator. I had a lot of pleasure looking at my undergraduate students doing that. But you guys are way over that. But I have the code to give you the test. I think the reason why we put the formula here is to let you know what comes into those confidence intervals, what is going to affect your test. So here, your confidence interval, the width of the confidence interval is going to be 2 times of this, right? If you want your confidence interval to be narrow, you want your confidence interval to be narrower, so it will be easier for you to make rejections. So if you want it to be narrower, increasing your sample size is one way. Having a homogeneous distribution by decreasing and decreasing the sample variance here is another way. Excuse me. And then if you change the alpha here, suppose you have a 99% confidence interval, it's definitely going to be wider than a 95% interval. So that comes in here. And this is the center of the confidence interval. If your difference is 0, then no matter what your level of confidence is, 0 will be in your confidence level. So those are the factors that's going to affect how your confidence will look like. So you can see that this is 90%, 95%. It's pretty obvious that this one is wider. So that's the two sample test with equal variance. When you assume the two sets have the same homogeneity, heterogeneity. But when you have different variance between the two groups, there's the two sample test for unequal variance. The difference is that instead of one value for the instead of pulling the variance of the two groups together in a simple way, you will need to use a very different way of pulling them together and calculating the degree of freedom. This degree of freedom will not be an integer, but you round it so that you can still check your t-table. So here we can also plug in the numbers in this two sample test. The same. Oh, I think I left out something. Oh, so for the equal variance, the confidence interval. After we have the confidence interval, we also have the test, right? The test it's just in a similar format of the confidence interval. You have the difference. You have the sample variance in the square root here. You would compare this to your t-table value and see if it is too large or too small. Too large means the two groups have very different mean, or this difference is very different from your null difference, the null parameter. And after plugging in the test statistic, you can check your t-table and you can also calculate your p-value here. So this is the two-sided p-value. You can also get the one-sided p-value by using just one of them or one minus this, depending on your alternative is. But I think it's just more convenient for you to use the built-in r-test. So now we can go to the unequal variance. It will just be a similar format, but the degree of freedom is more complicated. You also have the t-distribution, and after you plug in the numbers, you can get the test statistic, the p-value, and you can also have the confidence interval. So most useful thing that the function here, if you have two samples, you will put both x and y here, and you can choose which alternative you have. And for the equal variance test, you have this thing equal to true. Unequal test, you will choose it equal to false. And if you actually have paired samples, suppose instead of having, for example, you have a test of two eyes. one is the left eye, one is the right eye, and your data points are paired, you would use the pair test. Fail to use the pair test will still give you valid results, but if your data are paired and you make use of that in the t-test, you will have a stronger power. It will give you more power to detect the difference if you have the difference. So when you design your study, if you have the freedom to make your data paired, it's better than having unpaired samples. For example, suppose I do microbiome research. Suppose I want to see if the tumor tissue, the tumor microbiome, before the treatment and after the treatment, they're same or not. Ideally, I would want to take the sample from the same patient before and after treatment. But in some situation, you may not be able to operate twice on the same patient. But if you are able to, having those pair samples will give you more power, because the pair sample, you eliminate the when you compare samples from the same patient, you eliminate the other confounding factors, right? So the variation caused by the other confounding factors, those will not affect your comparison when you compare samples from the same patient. So pair test is very powerful, and you can use this option here. And this is one syntax of using the t-tags. You put one vector here from group A, one vector from group B here. In many situations, you will have your data in a data frame. One column for all of the LDL level, the other column for the indicator of group A or group B. In that situation, you do not have to subset your vector of LDL values. You can just use a formula. So, for example, your value wiggle and then the group. This will be the variable name for the column indicating the LDL values. This will be the column in the variable name indicating the column for the group. And you just put those two columns names here in the formula, put your data frame name here, and you will be able to do the t-test. And you can also subset your data frame. For example, if you have different hospital sites in your data set as well, then you can use that to subset. And do the t-test for each hospital separately. So here I have just the simple case where the data is stored in this data frame, and those two are the two columns names. And you will have all of the things that we described early on in the output. Any questions? So here, this is the unpaired test, and I can do this thing for, this is the equal variance test. This is the unequal variance test. And you will see their p-value is actually slightly different. They are not powerful. It's not true that one is more powerful than the other one. It's just different assumptions. The first one assume your variance is equal. The second one assume your variance is not equal. So which test to use? How do you know if if the two groups have equal variance or not? Well, there are tests you can do to check if the variance is equal or not. Here we have some rule of thumbs. You can calculate the sample variance of the two groups, take the ratio of the two variants. If the ratio is larger than 3 or smaller than 1/3, you can say, well, the difference in the variance is very large, and it's better to use, yes.
So what you said before, you can subset if you have, for example, different hospitals.
Yes.
So then you would have more than one t-test. Are you losing power, or can you put together and subset?
So if you want to only use one, this subset variable will allow you to only use data from one hospital and only calculate the t-test for that one hospital. It's just a convenient feature to use to subset your data frame instead of just creating another data frame. Yeah. But right, if you have multiple hospitals and you want to still do the same comparison, I would suggest a more complicated model, for example, a linear regression to account for the variation across hospitals. This is just a very simple test that only considers one factor. No problem. So the variance, we have equal variance tests and two unequal variance tests. And the rule of thumb to check if the variance is equal or not is to look at the ratio. And there's also a formal test for this. That's an F test. But all of these rule of thumb, the tests, they are dependent on the assumption that the data is normal. It may not be true. If your sample size is large, then fine. But it is still very confusing which test to use in reality. So among my colleagues, the consensus is that you can do both. So you can do the equal variance and unequal variance test. You can do both, and if they give you the same conclusion, rejection or non-rejection, both in the same direction, then it doesn't matter. But if the decision conflicts, then you would want to see how much risk you want to take. So generally, we want to take the more conservative approach and use the one that fails to reject. So because the null is the one that we want to protect. And you can also present both. Or I think this is probably the one that I would go with, is just to use the unequal variance, because this test uses less assumption on the data set. But if your data set truly has equal variance and you use the equal variance test, you probably will have higher power, slightly higher power. I don't think it's worth taking, so I would use the unequal variance test. Other people may have other opinions, so these other two options are also things you can consider. It's just a personal choice. And you can also use the variance ratio test. It's free you of making any personal choices. Any other questions? So this variance test can be done using the R function. It's pretty convenient. It's similar as the t-test. But alternative should be two-sided. Because you're trying to check their equal variance or not. So the variance ratio test, this one is not perfect because it relies on a normality assumption. It is actually very sensitive to the violation of normality assumption. So be careful if you want to use the F test. You need to have a very large sample size to truly depend on it. Any questions? So two sample t-test, and those are for normal distributions, continuous values. We also have very common situation where we want to compare two proportions. So if we have two sets of patients, and we want to see how much proportion of each group have the viral load under control, then this comparison of proportion will be the test to go. So I have simplified the steps. We will have a null hypothesis that will test for the difference of the proportion parameters. And this will, if you plug in the observed proportions, that's going to be your point estimate of the difference. And under normality assumption, you will have, well, under large sample assumption, the difference will have approximately normal distribution. So you can also construct confidence interval based on the normal assumption. So this confidence interval, when you see the z here, your data is not normal, it's proportion, but you have a z that's from normal distribution. That indicates you assume the large sample size. So if you have a small sample size, this test is not your friend. And in this specific case, we actually have a very large sample size for both groups, I think. So it's still safe to use the normality approximation. So the steps, I think it's getting a little tedious to go through every one of the steps. So let's just focus on the shape of the test. In the numerator, you have the difference of the two groups proportions. In the denominator, these are just quantification of the variance of the mean. So you know how large is large in a difference. This is related to the proportion. So if you have proportion that's very close to 0.5, this thing will be larger. If your proportion is more to the extreme, 0.1 or 0.9, this thing will be smaller. So this will also be reflected into your power. So your null hypothesis, when the null hypothesis is around 0.5, it's easier to test. When your null hypothesis is close to 0.1 or 0.9, it's actually harder to test. So here I also have the code for using R. This one actually do not rely on the normality assumption. So it's safe to use when you have small sample size. And you can see the results are slightly different from above. Oh, actually they are the same, is it? Huh. It's actually the same, so there should be an option. The option should be changed. I will get back to you after this class. I need to investigate the use of this function again. So we definitely need a test that's not dependent on the normality assumption. But here, this is just one step solution for all of the formula above. And if you have more than 3 groups to compare, if you have 3 groups and your null hypothesis is all 3 groups equal to each other, then t-test or z-test will not be sufficient. You will need to rely on a one-way ANOVA. So it's just another. It's a special case of linear regression. So the assumption is actually going to be all of them being normally distributed, and the variance will be the same across all of the groups. If you have different variance, then it's problematic. If you use one-way ANOVA, you automatically assume the variance is the same across all of the population. There is one test statistic to check if the variance is equal. If you do have a violation of this assumption, then some more complicated model need to be used. You might need to use some other fancier methods to get the group effect out of the variance. But that's not covered here. So one-way ANOVA, you just need to know that it actually assumes the variance is equal. But when you have unequal variance, you can specify here, and it will use some more complicated way to do the one-way ANOVA test for you. I guess I probably sound a little confusing here. So, anything that you want me to clarify? So, for one-way ANOVA, you have the observed values in the on the left. On the right, this will be the column for indicating the groups. Those two are two columns in your data frame. And here in this column, you do not have to have only group 1 and 2. You can have multiple groups. And you will have a F value here. If you only have 2 groups, so remember, by default, this variance equal is false. If you use one-way ANOVA with 2 groups and unequal variance, it's going to give you the same p-value as 2 sample t-test with unequal variance. So using one-way ANOVA and 2 sample t-test, you will have the same result. So when you have a non-rejection with 2 sample t-test, don't think that you can get another p-value for doing one-way ANOVA. You will not get that luck. They are just the same test. They have the same assumption. It's just 2 ways to construct the test statistic. But they will have the p-value, the same p-values. Question? So now we're going to talk about power and sample size. This will come in handy when you write your proposals, because as statisticians, we often come to the question of, is my sample size large enough? How much sample size do I need to get a power of 0.8? I once have a collaborator who asked me, I have a 3 versus 3 comparison. Is that going to be enough? And my answer would be, it depends. It depends on how homogeneous your patients are, and what is the effect size that you are expecting. If your 2 groups are super different, then maybe 3 versus 3 will be enough. But if you're trying to detect a very subtle difference, you might need a larger sample size. But many investigators are not satisfied with my answer, because they just want to know if 3 versus 3 is enough or not. There's actually a YouTube video dedicated to this situation. But I think after sitting through my really long lecture, you are wise enough to know that that is a very offending question. Right, sample size is a very tricky thing, but unfortunately, NIH always asks us to do a calculation of power and sample size in our proposal. And truth is, many of the investigators, well, I think the real sample size in many of the research studies is actually the budget divided by the per sample cost. And with that sample size, you try to calculate what is the effect size you're able to afford. Because that effect size is really unknown. You cannot really say what effect size you are going to expect from your study without some previous literature. So ideally, you would want to have infinite budget and calculate the sample size and power, but in reality, it's the other way. But still, these tools are still needed for your proposal writing. So we'll go over the power and the sample size calculation. So the power, remember, it is 1 minus the type 2 error. You would want to have a sample size that gives you enough power. That means you make very small type 1 error. The probability of making type 2 error. The power depends on your alternative, the difference between your alternative and a null. The effect size is reflected in this difference. And the tolerance for type 1 error is also in your power. If you have a higher tolerance for type 1 error, if your alpha is large, you can have more freedom to reduce beta, so you will have more power. Alpha, beta, they are a trade-off. Your sample size, larger sample size gives you more power. The variability of the data, more homogeneous subject group give you more power. This is also a compromise you need to make. So if you draw a sample, rich study, if you want to perform a study on a specific demographic group, for example, if you only want to focus on female, you may not need such a large sample size, but your conclusion will also be narrowed to only female. If you want to do it for both female and male and all these ethnic groups, backgrounds, your conclusion will be more generalizable, but you will need a larger sample size. So this is also some trade-off that you will need to make depending on your research question. And it also depends on the test statistic. If you have a good test, then your test will have a larger power even when your type 1 error is under control. But in the literature, you are mostly likely using the most powerful test that has been there used for so many years. So this is not something that you consider many of the times. But in a more complicated study, for example, let's say gene expression, differential gene expression, there are multiple methods there. DSeq, Lima, all the software packages developed for the same task. Some of them are better, some of them are not. And there are papers comparing these methods to show that how they can control the type 1 error and how powerful each test is compared to each other. So those are the more complicated situations where you actually have to choose a good test. In the scenarios that we're going to go over today, your test is already chosen for you, the one that's been there forever. Any questions? So in order to calculate the power, some of these factors need to be controlled. And for example, you can, for a fixed sample size and for a fixed type 1 error, you can calculate the power for several effect size, or you can control the type 1 error and the effect size and calculate the power for different sample size. So all these 4 parameters, fix 3, you get 1. Here, let's use the population mean as an example. So suppose we're trying to design a study to determine if HIV treatment also have an effect on a secondary endpoint. So instead of LDL, we're also looking at triglycerides. And if the triglyceride level is changed by 10 units, we want to be able to test this statistically. If it's smaller, we may not be able to test it, but as long as the effect size is larger than 10 units, we would want to have the sample size, the power to detect it. And our plan is to use the one sample t-test. If you use another, like a worse test, then your power will be different. So before you calculate the power or the sample size, you need to fix on one specific test. Here, I only have one choice. When I do 2 sample tests, I have multiple choices. So you will have multiple power calculation and sample sets for the different two sample tests. So the power calculation is actually related to the test that we use, because you can actually calculate the probability of type 2 error based on the test statistics we use. This is the event when we do not reject the null hypothesis. Your z-test is between -2 and 2. So this is the event of not rejecting the null, and this is when the alternative is true. So conditional on alternative is true, not rejecting the null is making a type 2 error. This probability is the probability of making a type 2 error. And you can then solve for y bar inside the whole equation here. This is the same event, it's just expressed using y bar. So this will actually help you obtain the power, because now you can plug in your effect size. So your effect size is reflected between in the difference between the null and the alternative. Remember, the null is 0 and the alternative is 10. So if you have an effect size of 10, you want to be able to detect it. The 10 is in the alternative here, so the 0 is in here. If you take 10 out of y bar, the y bar minus 10 will actually be a mean zero distribution. So I should probably rewrite it for you guys before the lecture, but this probability has the sample size in here, the effect size that's reflected in the mean and the alternative here, and it also has the type 1 error control in 0.96, because if you have 0.05 for alpha, you have 1.96 here. And you also have the variance of the population here. If you have all of these values, the effect size, the sample size, the type 1 error control, and the variance of the population, you can plug them in to get the probability of type 2 error, and 1 minus of this will be your power. So power, type 2 error, they sum up to 1. The more power means that you are less likely to make type 2 error. Here I read it out for you. I was doing a late night review of the lecture and forgot I already have it. So here, you can rewrite it inside. This will be your formula for the power calculation. So from the formula here, you will be able to know what affects your power. You can see that if you have a larger sample size, this whole thing will be larger or small. It depends on this difference here, right? But if you have suppose we have a positive number here, then a larger sample size will mean a larger value here, right? And that is actually which case? So mu is 10. This is the alternative. This is a negative one. So it should be this case.
I think you're looking for the next graph.
This one? Oh, right. Thank you. So when you have a larger sample size, you will actually have a power curve that's in this shape. So The larger sample size will give you more power. The red curve is the smaller sample size. Actually, it's also reflected here, because when you have in our situation, we have a negative value on the numerator. We have 0 for mu0, 10 for mu8, right? This is negative. So when you have a larger sample size, this will be a more negative value. And what this means is that you're taking a probability of, you're taking a chunk of the bell curve and calculating the area under the curve. And you will have, when you have a larger sample size, it will actually be more to the tail, to the left tail. So your beta will actually be smaller because you are moving to the tail of the bell curve and calculate the area under the curve. It's smaller area, so it's smaller beta and it's larger power. And vice versa, if you have a positive value on the numerator, you're calculating the area under the bell curve, you move it to the right end. It will also be narrower, a smaller area, a smaller type 2 error, and a larger power. So the sample size, when the sample size is larger, you will increase the power. And here, the alpha, if you have a larger type 1 error rate, instead of 1.96, suppose you have 1.65, then the band here will actually be narrower. So you will also have a smaller area under the bell curve, and this beta will be smaller. You will have a larger power. The population variance works in the opposite way of the sample size, so I'm not going to repeat it. And this thing, if this thing is larger, the absolute value is larger or smaller, you will also move to the more extreme of the bell curve and calculate the area under the curve. You can visualize this by looking at the bell curve here, but essentially you just really need to remember what are the factors that's going to affect your power. More sample, a more liberal type 1 error control, a more homogeneous population, a larger effect size. Those 4 will all increase your power. And sample size estimation. So when the power calculation is when you choose different sample size and calculate the power. Like I said, you can control the other 3 and reverse the role of power and sample size. You can calculate the sample size based on different power as well. So here I will just let's first go over the examples, and then we'll talk about the real life situations. So here I have a powerful power calculation for the proportion as well. We just talked about the power calculation for the mean. The power calculation for the population proportion is in a similar format. You first look at the probability of making the type 2 error, which is not rejecting the null when the alternative is true, and you write out the entire formula. Take 1 minus of it, it will be the power. And similarly, you will see the same dynamic of all the same factors that affect the calculation of power. You have the sample size, the type 1 error. But the difference here is that instead of the effect size and the variance, you have the proportion. Because for binomial distribution, the mean and the variance, they're linked. You only have one parameter that decides both the mean and the variance. So this pi 0 here will be the parameter that really affect your power calculation. So how is it going to affect it? Suppose I have pi 0 that's 0.5. What's going to be the numerator? It's going to be 0.25. If I have pi 0 that's 0.1, the numerator will be 0.09. So which one is larger? 0.25 is larger. And that means this whole band, this band is also larger. The probability is larger for the type 2 error. So your power is actually smaller for the situation when you have pi 0 equal to 0.5. So I correct one thing that I said early. It's harder to test if you have pi that's in the middle. It's easier to test if you have pi on the two ends. It's a little hard to remember those things if you do not do it very frequently, but that's why we have this formula here. If you cannot get your memory straight, you can go back to the formula and try to see how the parameter pi 0 affect the probability of type 2 error here. So the conclusion is that when you have pi 0 in the middle, this band under the normal bell-shaped curve is going to be wider, and your type 2 error is going to be larger, your power is going to be lower. Any questions? And the most important thing for you guys is to know how to do the power calculation using R. So this is the function if you want to do the power calculation for normal distribution and one sample test or two sample tests. You can do both. But the example here is for the one sample. So you have the difference, the effect size, which is the alternative minus the null. This is the value that you would expect to detect, the effect size you would expect to detect, but you need to divide it by the sample variance. This is something very often overlooked. When you plug in the effect size, you need to scale it by the population variance. And you can plug in the sample size and the significance level and leave the null for power to calculate the power. You can also leave the sample size as null and power as 0.8, for example, to get the sample size calculation. It will actually be the same function. You just leave those two things null differently. So in this case, we leave the power null, and it will provide you with the power when the other values are chosen like this. And you can do it for different effect size to get the power curve. So the curve is obtained by calculating the value of power for all different D here. And when you have D that's very close to 0, you will have lower power. So that when the effect size is very small, you will have lower power. When the effect size is very large, since this is a power calculation for two sample tests, for two-sided tests, you will have a larger power when effect size is either too large or too small. But you can also choose the power calculation for one-sided test by choosing the alternative here. Your power curve will actually not be a U shape anymore. It will be an S or the reverse S shape. So that's for the normal two-sided or one-sided test. And you can also do similar power calculation using these functions for proportion tests, one sample or two sample, equal or unequal sample size. So those are the different functions you use for different tasks. For the sample size calculation, we'll use the same function. But it is very important, like we did for the power calculation, you need to know what test you use, whether you're doing a two-sample test, a two-sided test, one-sided test, equal variance test, unequal variance test. Those will all affect your power calculation and sample size calculation. And in some situations, you do not have enough budget. You just have to write an effect size that's super large or a power that's not very large. By decreasing the power from 90 to 80, you may have a big reduction in your sample size required. So here, we are going to look at this sample size calculation for the detection of 10 unit change for triglycerides. So we are going to, for example, say we want to have a power of 90%, which is pretty large. And then the variance, this is going to be needed just like the power calculation. And sometimes it's just very hard to come up with a sigma here. So what I have seen is that you when you state the effect size in your proposal, you actually state it in terms of the standardized effect size. So in order to detect a standardized effect size of what, if you state it that way, you are actually using this as your effect size. If you use this as your effect size, if you say, I want to detect 10 units of change, then you have to come up with a number for sigma. And sometimes you may know it from previous literature, sometimes you may not. In this situation, if you are fixated on the 10 unit change, you will have to come up with the sigma. So it can be, it's generally done through a preliminary data set or some existing literature. And also, in some situations, you have something that you want to measure that's actually already surveyed by the population. For example, you know the range of this value in the population. Then you can refer the variance estimate by dividing the range by 6, or this is just a rough estimate, because in many of the distributions, if you have the normal like a distribution that's very similar to normal, if you do a data generation, the range of the normal distribution sample will roughly be 6 times of your standard error. So that's why this is also something that you can use for your sigma plugin. So previous studies, pilot studies, range of the value, those can be used to infer the sigma. If you do not have any of those, you probably have to state your effect size in terms of the standardized effect. Any questions? Yes. It depends on whether you have intervention in your longitudinal study. Can you give an example?
So I do mouse work,
Mm-hmm.
and some of the experiments I do are behavioral testing in different times. And mine, like the differences increase over time in the group. So I don't know, for these I think I just need to choose a time point and then calculate based on that time point that I can consider all.
That's a good question. So in your situation, your effect size change across time. It depends on what time point you want to detect that effect size. If you're more fixated on early time detection, you will use that as a reference. Yeah, that's a very good question. Any other questions? So some other consideration, do you have enough sample size? Well, actually, do you want to use T or normal distribution to calculate the sample size? So most of the times we would use T distribution, but like the T distribution has a degree of freedom in there, right? When you use T distribution to calculate the sample size, there's a chicken egg problem. What degree of freedom do you use for the T distribution? So the software will help you solve that problem by trying different sample size in the backstage and spit out the result. But for hand calculation, you would need to use a normal distribution as the reference to calculate the sample size. But regardless of what you use, the Z or the normal for your sample size you can use either T or normal to calculate your sample size, but eventually you will need to still do the T test instead of the Z test when your sample size is actually not that large, because you don't know when you get the data what your sample variance is going to be, and whether your sample size is going to be large enough to use a Z test instead of a T test. So T test is safer. The general formula, for example, for the population mean here is this. So you have the formula is also given to you to understand what are the factors that's going to affect your sample size. Again, you have the type 1 error, the type 2 error, the population variance, and the effect size. So effect size, when the effect size is larger, you need a smaller sample size. When you have a larger population variance, a heterogeneous sample, you need a larger sample size. And by decreasing type 1 and type 2 error, you will also need to increase the sample size. Those are the factors contributing to your sample size calculation. And this is for one sample T test. And we also have the one sample proportion test. The sample size calculation also have all of the factors that we mentioned earlier, type 1 error, type 2 error, and the effect size is reflected in the difference between null and alternative. Your sample size will also be dependent on the location of your null. So like we said, when your null is very close to the center of 0.5, you will need to have a larger sample size, because when you have 0.5 here for pi 0, this is 0.25. When you have 0.1 for pi 0, this is 0.09. So you need a smaller sample size when your pi 0 is very close to the end. That's the formula, and you will also have the function ready for use. So here we have the example for normal distribution using the code that we using the formula, just translating the formula that we have into code. And if you use our function, you will get basically the same result up to some precision issue. So when you plug in the normal effect size, remember to divide the population variance. The difference between those two is this one is dependent on t-test. This one is using the normal test for the power calculation. And you can see they are slightly different. this t-test is slightly more conservative. So you would need 2 more subjects if you base your sample size calculation on here. And if you want to do the proportion test, the 2 proportions need to go in this function to calculate the effect size. So you do not put the effect size 0.5 minus 0.4. This function will translate your effect, the 2 numbers, the null and the alternative, into an effect size here. So this is actually the effect size that's calculated. And the sample size corresponding to it. When you write this in a proposal, you will say that assuming that null is 0.5 and we want to detect the change if the alternative is at 0.4, you do not have to write this number in your proposal, but you need to use this function in the p-dot test. Any questions? I guess I've finished all my materials today, and we'll give you some time to experiment all these codes on your laptop, which I will do the other teachers do if they have time left.
I think you usually call it.
Yeah. It's a long day for everyone, right?
Yeah, that's the point. Yeah, I don't think there's like a coding example, right? Or like exercises.
Yeah.
So, yeah, that's usually. So, unless you want to stick around and work through them and help out.
Yeah. And I will stay here longer if you have any questions that you want to ask, because these are pretty abstract things. And you're very welcome to come with your own research example and put it into the context. All right. Yes. It's the same. Yeah, numerically it's the same. So I wanted to make sure, actually I tried it last night.
Yeah. So there's something for what we want to detect in or what is the physical meaning of the value.
So in the power calculation, there's a what was your question?
Yeah, this function, what is the physical meaning of 0.5 and 0.4?
I think one is a null and one is the alternative.
Okay, so
Good. I probably need to look into the manual. I didn't think that it should be symmetric, but it seems like it is.
right. And then my other question is, sometimes people ask for calculating sample size in the microbiome data, and I'm like, there's really not a good method. Do you know if there's a good method?
You don't know the effect size, right?
The effect size is unknown, the variance is so highly variable, and then I'm like, I don't know, but
I know.
Is there a good way to estimate sample size for microbiome data, or do we just need to wait until more studies is done?
I would suggest that look into the literature and use some studies as example. For example, you can say that this study was able to detect the effect of like gut microbiome change on the behavior of the kids using a sample size of this and for this age group, and that's going to be our reference, and we'll have a comparable sample size. That's what I did.
Okay, but like, what exactly would the effect size be? Is it like when you say
it's impossible because you are going to use a more complicated test as well. Instead of a two sample t-test or p-value proportion test, we are going to probably use seek.
Right.
And there are many things factored into the test. But I think in my experience, we'll just simplify the scenario. We'll say that with this sample size, if you want to detect a change of composition of a certain bacteria, for example, you can transform the composition of a bacteria into the proportions, right? And you can say if you expect to see the proportion to be changed from this value to this value, and variance. Wow.
I feel like people don't give various approaches, and then like when you say the composition is different, it's like, are you using Fermat-Nova, or are you using beta diversity metric?
I've actually never calculated the power calculation for.
So I have like.
Did I went through this whole ordeal for one of my proposals.
Because I think NIH is starting to require power calculation for everything, and I'm like,
I hate it.
Know what to do.
Because normally it's just the budget over.
Right, it is the budget. And like, and with microbiome, unless you're doing a big genetic study, it's such a shot in the dark. And I'm like, I don't know what I'm looking for.
Yeah, so that's why I was very hesitant. I don't like the power calculation for microbiome.
Yeah.
So Richard, have you had any power calculation for situations where you don't know the effect size and the variance at all?
I mean, what I've done is just generated it under like, I'm assuming probably just like a ton of different scenarios, like either based on the literature or something like that, and then just visualize them and be like, if this scenario, like like a plot, right, or like the x-axis is maybe the mean, and you have like different lines for different variances. Something like that.
I was thinking about microbiome studies because that's the field I'm in, and then like trying to estimate sample size for a given power in microbiome studies. Like I don't know how that's gonna be done.
Yeah, I don't know either.
Well, it's good to know that I'm not the only one that's wrong.
Yeah. So, but I don't know. That's what I typically done. Right? I'm trying to think about. I did something from past.
Yeah.